Imagine being pulled into a place where the very laws of physics no longer apply, where time, space, and reality itself are stretched, twisted, and crushed into something incomprehensible. This isn't science fiction. This is the reality inside a black hole. For centuries, black holes were only theoretical, dark stars so dense that not even light could escape. Jean Michel first imagined them in the 18th century, but it wasn't until Einstein's general relativity that we realized these cosmic monsters were real. They aren't just holes in space, they are gateways to the unknown. But what really happens inside? How does matter behave when gravity becomes infinite and time itself comes to a standstill? Even the most brilliant minds, from Einstein to Hawking, have struggled with this question. Black holes represent the ultimate conflict in physics. General relativity says one thing, quantum mechanics says another, and inside, both seem to fail. Today we're going to travel past the event horizon, beyond what is known, and explore the most extreme environment in the universe. Prepare to leave the familiar behind and step into a place where the universe is rewritten. As we approach a black hole, the first invisible boundary we encounter is the event horizon, the point of no return. Cross it, and escape is impossible. Not because the black hole pulls harder, but because the fabric of space-time itself has twisted so drastically that all paths lead inward. Light, matter, even time itself cannot turn back. Imagine standing at the edge of a waterfall, but instead of water, the universe itself cascades toward a singular point. That's the event horizon, a line that marks the boundary between the known and the unknowable. From the outside, you'd appear frozen, stretched out forever by gravitational time dilation. But for anyone, or anything falling in, the journey is terrifyingly real. Here, gravity is no longer a gentle pull. It stretches you lengthwise and compresses you sideways in a process physicists call spaghettification. Your body would elongate like a strand of pasta, pulled apart atom by atom as you approach the singularity at the core. Even light cannot escape the crushing gravity. Space bends back on itself, creating the ultimate one-way escalator to destruction. This isn't just theory. Observations of stars orbiting supermassive black holes, like Sagittarius A at the center of our galaxy, confirm the immense gravitational pull. Simulations show the tidal forces would grow exponentially the closer you get. And yet, here at the event horizon, physics itself begins to break down. Even in this terrifying environment, scientists have found ways to peek inside. Stephen Hawking proposed that black holes emit faint radiation, now known as Hawking radiation, a whisper from the otherwise silent abyss. These clues hint at the delicate dance between gravity and quantum mechanics, even where the laws seem to crumble. Past the event horizon, everything changes. Space and time themselves swap roles, guiding all matter inexorably toward the singularity at the black hole's core. Here, the known laws of physics crumble. Density becomes infinite, volume shrinks to zero, and gravity grows beyond imagination. This is the ultimate cosmic paradox, a place where even Einstein's equations fail. The singularity is not just an object, it is a point where reality itself fractures. General relativity predicts infinite curvature, while quantum mechanics insists that information can never be destroyed. Reconciling these two has been the greatest challenge in theoretical physics for over a century. Scientists call it the black hole information paradox. To grasp the scale, consider Planck length, 1.6 times 10 to the minus 35 meters, the smallest meaningful unit of space. A singularity compresses matter into a region smaller than this, where our current understanding of time, distance, and causality no longer makes sense. Space becomes a seething quantum foam, twisting and folding unpredictably, like a stormy ocean frozen in a fractal pattern. Even photons, particles of light, cannot escape. Yet quantum theory suggests that information about what fell in must somehow survive. Theories like the holographic principle propose that the three-dimensional interior of the black hole might be encoded on its two-dimensional surface, like a cosmic hard drive. Some speculative ideas go further. Could black holes be portals to other universes? Could they harbor white holes, their theoretical opposite, spewing matter outward? These notions may sound like science fiction, but they emerge naturally from equations attempting to reconcile gravity with quantum mechanics. What's certain is that a black hole's singularity represents a limit to human knowledge. It is the ultimate challenge for scientists, a place where our models break, where time ends, and where the universe forces us to confront the unknowable. Yet, it is also a window into the deepest truths about existence, a laboratory for the fundamental rules of reality itself. If the singularity is the heart of a black hole, then its edges are the boundaries of human imagination. Modern physics offers glimpses but no certainty. One of the most provocative ideas is that black holes could be connected to other regions of the universe, or even other universes entirely, via wormholes. These hypothetical tunnels through space-time might allow matter to escape, bending reality in ways we can barely comprehend. Another concept shaking the foundations of physics is the firewall hypothesis. It suggests that the event horizon itself could be a searing wall of energy, incinerating anything attempting to cross. This idea arises from the struggle to reconcile quantum mechanics with relativity, a reminder that black holes may not be the silent monsters we once imagined, but active extreme laboratories for the cosmos. The holographic principle adds another layer of mystery. Perhaps the three-dimensional interior of a black hole is fully encoded on its two-dimensional surface, a cosmic blueprint of everything that has fallen in. If true, the universe itself could operate like a vast hologram, with black holes acting as critical nodes in a vast informational network. Some theorists even explore the possibility that black holes are remnants of previous universes or seeds for new ones, part of a grand cyclic cosmos. In these models, the death of one universe gives birth to another, with black holes as the midwives of cosmic rebirth. It's a staggering thought. Inside every black hole could lie a universe waiting to be born. No matter the theory, one truth remains. Black holes challenge everything we know. They push the limits of human understanding, forcing us to confront questions that may never have answers. And yet, this is precisely what makes them so fascinating. They are not just voids of destruction, they are mirrors reflecting the deepest mysteries of existence. Even after decades of study, black holes remain among the most mysterious objects in the universe. Thanks to observations from the Event Horizon Telescope, we've seen the first direct image of a black hole's shadow, confirming predictions from Einstein's theory of general relativity. We now know that black holes come in different sizes. Stellar black holes form when massive stars collapse, containing a few times the mass of our Sun. Supermassive black holes, millions or billions of times heavier, sit at the centers of galaxies, including our own Milky Way. Their gravity shapes entire galaxies, controlling the motion of stars and gas. Hawking radiation, predicted in the 1970s, suggests that black holes slowly evaporate over time, losing mass in a process that takes longer than the age of the universe for the largest ones. This leads to an unresolved puzzle. If black holes evaporate, what happens to the information about the matter that fell in? Researchers are still debating, testing ideas like the holographic principle and quantum gravity models to answer this question. Gravitational waves have added a new dimension to our understanding. When black holes collide, they release ripples in space-time, first detected in 2015 by LIGO. These signals allow us to study black holes without seeing them directly, revealing their masses, spins, and how they merge over cosmic time. Scientists continue to simulate black holes using supercomputers, mapping how matter and energy behave near the event horizon, testing relativity under extreme conditions, and exploring what happens at the singularity. Every new discovery pushes the limits of physics, giving us clues about the earliest moments of the universe and the fundamental nature of space-time itself. From the point of no return to the birth of new realities, the journey into a black hole is a journey into the heart of creation and destruction. They are nature's ultimate laboratories, where the rules of our universe are broken and rewritten. Thank you so much for joining us on this cosmic adventure. If you enjoyed this journey into the unknown, don't forget to like, subscribe, and hit that notification bell for more mind-bending science. See you next time.